All right, well, let me just tell you, I didn't know that this was going to be quite this way. I like to use the board. My name is Mike Begensky, I'm your professor. And in emag 2, we're going to be covering the last part of Dr. Wentworth's book. First, I want to make sure, I sent everybody a link. Did you all get that? All right, are you able to access that and read it? All right, if you have any questions about that, let me know, because it's pretty self-explanatory. I like quizzes every week. I give you homework and I supply answers, but the reason I like quizzes is because with homework you can get 5, 6, 8 people working together. One person's doing the work, everybody gets credit for it, and very few people learn that way. Now, I do know there are people that do their own homework and they benefit tremendously. I'll give you homework problems, but I'll give you the answers or answer solutions, both. So you can go through and work them, and I suggest you work them right before the next class period, right? And I'll make myself available to answer any questions as best I can. This is really a big class, and I hope it doesn't get too hot in here, but if it does, we'll open the doors. And I hope that thermostat works. What is it set on, out of curiosity, if you can see it? What is it? 70.
It doesn't work.
All right, well, we might bring it down a notch because there's so many bodies in here, this place is going to heat up. What I like doing is having two midterms, one final. Each midterm is worth 20% in this case. A final exam is worth 30. The homeworks, or really, I should say, the quizzes are worth 20%, and there's a 10% MATLAB project in there, if you take a look. All right, now, has everybody here worked with MATLAB? If you have not, raise your hand. If you have not. You never have used MATLAB? Have you used Octave? Have you used Python?
No.
All right, well, MATLAB's a thing that some people curse, other people love, but the reason I think it's good to get exposed to it is because almost every group that I know of, I've worked at NASA, Eglin Air Force Base, the Naval Surface Warfare Center, was on the carrier Eisenhower, let's see, Redstone Arsenal, at the NASA facility at Langley and Redstone, everybody uses MATLAB, and so does most people like Intel if they're going to be doing any kind of numerically intensive programming that requires optimization or something like that. Otherwise, they use Python because Python's free. How many of you use Python? All right. You can use Python for these projects, but personally, MATLAB is better. It's seamless. I will tell you this much. The nice thing I like about MATLAB, just to give you a heads up, you don't understand something, go to YouTube, type MATLAB plot. You'll get 1 million people that can help you with it. MATLAB, optimize, using genetic algorithm, anything like that, it's there and it's readily available. Most of the things you learn in engineering, what you really learn is how to learn, to be honest with you. Because when you get out there in the real world, you're going to find out that you're going to be learning far more than you're learning here about very narrow subjects areas usually, and you'll find out you're going to be the world expert at the end of it a lot of times. Now, MATLAB is something that there is a student version of MATLAB, and I don't know how much it costs. Does anybody know?
It's $50.
That's not a lot. $50, less than a textbook. I recommend you get a copy of that for yourself, and this is my own personal beef with using anything that requires a FlexLM license. This is me personally. A lot of times it's slow or you'll get dropped. I have a FlexLM MATLAB license with Auburn University, and it has caused me more headaches. I'll be doing something and then just freezes, lose everything. And it's because this FlexLM, it has to refresh and has to really authorize the use of that tool. And there's only a limited number too, by the way. So if you can avoid a FlexLM license, in other words, a license from a server that's not yours, do so. And so I encourage you to get the MATLAB, or get Octave. Does anybody know what Octave is in here? All right, Octave is slower, but it'll do the job. All right, and it's free. So if you're that much of a cheapskate, get Octave. And Python's free too. Python will do most of the stuff we do here. It won't do everything, but Python's pretty good. And you'll see in industry, my wife was at Intel, she told me that they use Python exclusively for everything, but you know, when you get into programs that require a lot of matrix manipulation and things, then you go to MATLAB. And that's what MATLAB's designed for. And I use it all the time. All right, now, this book is what we're going to use. And I'm going to reference things in here. Homework, I may give you other homework problems. I think it's a very good book. The problems are not difficult. These are very low-level problems, in my opinion, compared to some, and I'll supply you with more challenging problems. This is another thing that's on the syllabus, but I might as well tell you this. Every test and quiz is closed book, closed notes. Because of the size of this class, I'm probably going to have to make out 2 and then pass them out every other, like A, B, A, B, just because you're thick as sardines in a can. There's no room to spread people here. It's closed book, closed notes, all right? You can use your calculators, but no wearable electronics or phones. I've caught kids doing this. I hate to see them getting all in trouble. They get a F for the course and stuff like this. You don't want to do that. And if you go up to that academic dishonesty thing, I don't know what happens. I've heard all sorts of different things, but I've never had anybody expelled, but I got one guy really got in trouble and had to write a long report about all cheating in general. And it was horrible. So don't do that. It's not worth it. The thing I'm going to tell you about, and I always tell people this. This is from personal experience. It happened to me when I was in college. I had a professor that basically knew, he was in psychology, what we wanted to know. We wanted to know how to learn. Some of you have heard this. If you're an engineer, you're going to study differently than a fine arts major trying to create a statue or something. It's just the nature of the problem. You're analytic, deductive reasoning. You have to have an element of creativity. But here's the thing, after about 50 minutes of intense work, you're going to start fatiguing and start making mistake after mistake after mistake. Take 5-10 minutes off. See if this doesn't help you guys. 5-10 minutes, just don't do anything, play ping pong, I don't know, watch whatever, a football game, then go back and try to work as best you can without any distractions. Some of you will not care what I say. You're going to be listening to music in the background and have your girlfriend talking to you and stuff. But if you can isolate yourself and go for 50-minute stints and take about 5-10 minute break, you'll be amazed at how you improve your performance. And also sleep. Trust me on this one. The U.S. military spends probably billions of dollars trying to optimize the performance of like everybody, Navy SEALs, U.S. pilots and all that stuff. This is what you need to know about hardcore analytic thinking. Even the very best chess players do that. They take a break. So I'm going to tell you that. Because you just get into a mode where you produce nothing except dumb mistakes. The homeworks, I usually assign basically 4 to 6, 7 problems. It's about an hour and a half to 3 hours worth of homework every class period. And some people can get it done in 10 minutes, 20, 30 minutes. There's some remarkable students. Others need to struggle at it and learn how to do it, because that's really how you learn how to take tests and how your grades are going to be really. That will have more to do with how you perform on a test than anything in your final grade. The other thing I'm going to tell you is about the MATLAB project. I announced this in the last third of the course. I try to get one so there's a fair amount of variability in terms of the solution. You can't just cookie cutter it. And I try to get one that's unique to you. One of the ones, just tell you this, give you a little background. I had one where I wanted people to design a phased array, and the number of elements and the orientation of the elements had to do with their name. So everybody had a different phase array. And that meant when they did that, they actually had to get the initial beam pattern, and I'll explain that more later, with no phase change. And then I wanted them to take that and I think I wanted them to do something where they created a main beam with a certain amount of gain and scan it. And see, that's unique to everybody. And it also causes a lot of angst because nobody can copy anything everybody can copy MATLAB, but that's about it. Some formulas I give you, almost all things I expect you to know just by redundancy. If you do problems over and over again, you don't need flashcards for formulas. They'll be in your brain, just like V equals IR, things like that. If you forget that as an electrical engineer, you need to change majors. All right, now, I would love to use the board if I only knew how, but I'll try to use this and see how this goes. We're going to start in chapter 6, but it's a review of 5. We're going to start with Maxwell's equations. Are you recording me here? Oh, that's the other thing. I'm glad. I'm sorry I'm not at the board, all right? I always do this. I don't know if he mentioned this to you before I got here. I try to get one person who will record video and audio of the lectures, and then I put them on OneNote. All right, I can put the link on OneNote. You're going to use YouTube or Facebook? YouTube. And that way everybody can go back. If you miss a class, if you want to see what I said, if I made a mistake, you'll find it and let me know. but it really, I think, is beneficial. And you can also, the one other thing too, I don't know if you can do this for me. In a class this size, it might work. I've had before Facebook pages for courses like this, and I'll have students, somebody post a question, and other students will answer and interact. That's fine. I think all the interaction you get is fine with me. If you want, can you get a Facebook page with this too? All right. That way they can link to it, and I can help you with that. And if you have any other suggestions, now I don't use Canvas. All right, I got my own reasons. I've had more problems with Canvas shutting down on me, and problems with. Has anybody else had access problems to Canvas, or is it no? No? Well, I'll tell you, on my end as a professor, when you're loading things, sometimes it just doesn't work. I mean, I've had unless maybe now they've got the bugs out, but I don't personally like Canvas. Not only that, the university, for whatever reason, could shut that stuff down. This is out there permanently. You can look at this 10 years later, hopefully, unless you take it down. Because I always let the students run this part of the show. Are there any other questions, by the way? I prefer you don't bring anything that goes crunch in here, like potato chips, things like that makes crumbs, crackers, anything. If you want to bring a drink, I don't think you're supposed to have beverages in here. No, don't worry about it, all right? I don't care. If you want to bring coffee or something, just make sure you don't spill it. Or if you do, you clean it up. I prefer, if you want to bring a candy bar, fine, but I prefer you don't make a mess in here, all right? So if you bring Chick-fil-A in here, some pizza, it may not work. All right, eat outside. And there's, I usually get in the size, this class this size, 1 or 2 people that use some form of tobacco. If you are going to dip, see me after class. We'll have a little conversation about that. Because I don't know what is it about pop bottles and dip, but they spit in them and cork them, and if they ever spill, and it does happen, it changes the whole environment. All right. Now, on to chapter 5 in Maxwell's equations. All right. We'll start, and if you want to know where I am, or not, in chapter 6, pardon. Chapter 5, everybody had Maxwell's equations, right? And did y'all get through chapter 5 with whoever taught it? Has anybody not got through chapter 5 in Whitmore's book? Y'all have? I hope so.
I think we started that chapter.
Chapter 5 is the one where it's time-varying fields, where you get transformer action, induced EMF. I think everybody's had it. And then you were exposed to the full Maxwell's equations. I'm going to start by writing the full set of Maxwell's equations down and the coupling between them. And tell me if you can or can't see. Oh boy, how do I reduce the size of this? Let me just see here. Oop. All right. Just let me know if there's a problem. Besides the obvious one. All right, I'll try to do this. Yell at me if you can't see. All right, these are Maxwell's equations. The first is curl of H is equal to J plus the partial of D with respect to T. Now, here, H is the magnetic field. H has the units of amps per meter. J is the current density. It has the units, all these are vectors. That's going to be amps per meter squared. D, anybody know what D is? It's the electric flux, right? And density, electric flux density. That's going to be, well, really, let me do it this way. D is equal to epsilon E, where epsilon is the permittivity, right? And the units of E are volts per meter. Epsilon is farads per meter. D is coulombs per meter. I'm just trying to put the units down there. Epsilon is something that it really identifies how much energy free space can store in terms of electrostatic energy. The larger the value of epsilon, the larger the amount of energy in a given cube of space it can store for a given electric field strength. And epsilon in general is equal to epsilon relative, epsilon naught. I'm sorry about my penmanship. But you all follow me on this so far, class? Can you all read it? All right, now this is the first Maxwell's equation. This is what we usually do. I'm going to put all the coupling in here, or the relationships between each of these quantities. So J is called the Anybody remember? J is the current density, right? And J is equal to sigma E, right? And does anybody remember what sigma is? Conductivity, right? Y'all remember that? It's the conductivity. And J sigma E, right? And then we have D equals epsilon E. These are some relationships. I'm going to put another one down right now. B is equal to mu H. And by the way, mu is equal to mu relative times mu naught. Do you know what mu is, people? Mu is the permeability, right? And mu relative just is something that is a relative increase or decrease in the amount above free space. Mu relative, usually for magnetic materials, is say 100 to 1,000 or more. It's sort of like epsilon relative for things with a high dielectric constant, like silicon dioxide and things like that. Anyway, this is the equation I'm focusing on, I'm going to work with. The next equation, that's, by the way, that's Ampere's law. The next equation is going to be Faraday's law. It's Faraday's law of induction. Faraday's law of induction is curl of E is equal to minus dB dt. That's one where transformer action comes. These two are the basics. These two represent Maxwell's equations in the time domain. They are the most pure form of Maxwell's equations. They are in the SI system of units, this and this. Now, we're going to go to the phasor domain in a second. Can y'all read this, by the way? I look at some people struggling. That's curl of E is equal to minus dB dt. And B, by the way, I put it here, but the units of B, if you're wondering, are Webers per meter squared. It's a density, magnetic field density. So now what usually happens when you're involved in this type of effect is we go to something where we go to the phasor domain. Are y'all familiar with that? Usually we don't work in the time domain unless it's transient analysis. And transient analysis for Maxwell's equations requires a computer in almost all cases. Because these del square, really the curl of E and curl of H, are operations that in general have derivatives in X, Y, and Z if you're using Cartesian coordinates, and H and E have actual vector components in X, Y, and Z generally. And a time-varying solution of that kind of a problem is going to be basically 9 or more differential equations solved simultaneously for a variety of boundary conditions. You need a computer. Now you can simplify it, and we're going to get simple solutions that are generally applicable to certain situations. But transient analysis of this stuff is a mess. So we usually go to the phasor domain. And here's what I mean by that. Y'all remember back in the day when you had circuits, I like to start here. You had plus to minus something, and you would have something like 10 times cosine of, say, omega t as a voltage right there. Y'all remember that? Then you had a resistor here maybe at some value of R, and you had an inductor here, L. And you were after the current I of t, right? Now, you could write differential equations, right? You could say this voltage here, 10 cosine of omega t, would be equal to I of t times R plus L times di dt, right? And you could solve for it. You could use an integrating factor if you wanted to. But the way you were taught to do this when you had Dr. Irwin or whoever you had for circuits is you turn this thing into a phasor. You make it 10 at an angle of 0 degrees, right? That's what you did. I'm refreshing your memory on phasors. Then you put that resistance down. That is the impedance of a resistor in the frequency domain, right? And at this point, because it is a constant frequency, that omega is not something that's varying. It's a constant, like 377 or 120 pi, follow me? Radians per second. Well, now what you did is you replaced this inductor, where the voltage across an inductor used to be L times di dt, right? You replaced that with a simple impedance element. And you said this inductance is just going to be J omega L, and that would be an impedance, right? Y'all remember this, guys? Please work with me on this one. Don't think I'm doing this just because I need to kill time. I know that a lot of people don't understand this. I've taught this course too many times. Now, if you wanted the current here, you could get the current, but it would be a phasor current. Do y'all agree with me? All right, it would not be a time-varying current. It would be in the phasor domain. And that current would be what? I think Gross does this. How many have had Dr. Gross? All right, Dr. Gross is the biggest nitpicker about detail that I've ever met in my life. And you can tell him I said that because he knows that. Sometimes he'll drive you nuts with it. But anyway, if you wanted to get that, he always says it's a vector and a phasor. You put a tilde over, something like that. He is somebody that should work for, I don't know, drug distribution company or something. Somebody needs, well, you need precision always. Anyway, I here would be the voltage. In this case, I chose 10 at an angle of 0 degrees divided by the sum of these two because they're in series. Does everybody realize that, class? So it would be just R plus J omega L. And that would give you a current, right? Now, if I give you the values of omega R and L, you could give me an actual value. But what we like to do is always use polar form for this. So it's going to have some magnitude of that I, and it's going to be at some angle, right? Another way to write that is magnitude of I, e to the j angle theta, and that angle theta just has to do what the angle associated with that number is. Does everybody follow me on this, class? Your calculators do polar to Cartesian or cart to polar very easily, don't they? So it's not a problem. Now, once I have this right here as my I, if I wanted the time domain form, do you remember how to get it? This is where a lot of people don't. If I wanted to go back to the time domain, technically what you do is say that I in the time domain, I of t here, would be equal to the real part of the phasor form of I, and I'm just going to put I vector phasor times e to the j omega t. That's what you do. Now the real RE just means you only take out the real part of that. If it was 10 plus J5, you would just take out the 10. Do you follow me, everyone? Now, so everybody knows this. So I've catch some people don't know Euler's identity at this point in their career. Euler's identity is what? E to the j of anything, if omega t in general, is cosine of omega t, right? Plus j sine of omega t. Do you all agree with that? Just so you know what I'm doing. Now, when I take this right here, this I of t is actually going to be the real part of I. Well, it's magnitude of I, that's strict real. Then I have the phase angle, so it would be e to the j theta, but I also have omega t here, so it's going to be theta right here plus omega t would be in the exponent. It would be e to the j theta plus omega t, and that theta came from the current, right, class? Y'all follow me on this? I'm sorry if it's not clear, but y'all see this back in the back of the room? Okay? Now, when you take the real part of this, you see how you could expand that in terms of a cosine of theta plus omega t plus j sine of theta plus omega t. How many see that? Y'all do, right? All right? The real part is only the cosine term. So the bottom line is now I of t here is just going to be equal to the magnitude of I times cosine of omega t plus theta. And I reviewed that for one reason. Some of you are going to go to interviews, and this is a question they ask. They're going to show you a circuit with something like a cosine or a sine in there, and they're going to ask you to show them how you would solve the circuit. Now, if you're a physicist, you probably write a differential equation to solve it, at least some physicists. Is there anybody here with a minor in physics? A major in physics? Aren't you? Don't you have a minor in physics? No? Okay. Never mind.
About to start one.
What?
So I was about to start one.
Well, if you do, you might solve it using a Diffie Q because you like to beat yourself up. I'll probably get a letter from one of these guys over time. Anyway, that's why we do it in electrical engineering. Now, you'll notice there was no spatial dependence. Do you follow me on that? What we're going to do is the same thing, only there's going to be spatial dependence, and that's where I'm about to go. But I'm doing this first so you know what phasors are. So I got to go to the next page. So next page on this one, I'll call it page 2. Now we go and we're going to get a single equation with a single unknown. And I'm going to start by rewriting both of these equations in terms of just two variables, E and H. So first with the curl of H equation, I have curl of H equal to J plus the partial of D with respect to T. That's the first one. And the second equation is curl of E is equal to minus dB dt. And now I'm going to do this. I know that J is equal to sigma E, right? D is equal to epsilon E. It's an epsilon. I know that B, pardon me, I know that B is equal to mu H. And now what I'm going to do is stick these in here. So the first equation becomes curl of H is equal to sigma E plus epsilon times the partial of E with respect to T. I'm assuming epsilon is not time varying, so I don't have to take the derivative of it. Follow me on this class? So D becomes epsilon E, and the only time derivatives are going to be operating on E. That's going to be the first equation. And then I get the curl of E is equal to minus mu times dH dt. Now I have two equations only in E and H. Do you follow me? To solve this in any meaningful way, I want one equation and one unknown. Does everybody hear me on that one? One equation, one unknown. Anybody, some of you I know this. Anybody want to take a guess what I'm going to do? Well, tell me what to do. Any ideas? I bet you some of you know this. You just don't want to say anything because you look like smart aleck. Or you look too smart. Anybody? Going once, going twice. All right, how about we do this? We take another curl of this, so I have curl of E is equal to minus mu times d dt of curl of H. You all see that? That's a curl, and that's supposed to be an E, not a very good one. Let me try this marker. Y'all see what I'm doing? Can you all see that's curl of E is equal to minus mu times d dt of curl of H? Well, curl of H is what? It's right there, isn't it? Now, isn't that only an E on this side of it? So now if I replace that with this, now I'd have a single equation that is only an E, a differential equation. So now I have curl of E, and by the way, curl of E can be rendered as this. It can be the gradient of the divergence of E minus del squared of E. That's what this actually is. It's a definition, it's a proof. If you've had vector calculus, you'd have these things, but a lot of you didn't. You've had Stokes' theorem though, didn't you? All right, did you have these theorems at all, or no?
It probably showed up in account.
Did you have Green's function? Any of that?
Yeah.
Sort of?
It's been a while, but yeah, I think so.
Or you've been exposed to this. This isn't the first crack at this. It's real important you understand this. This is a vector identity. You don't need to be worried about this stuff. I'll give you this information, the vector identity, if you need it, all right? Comes down to that, and that's equal to minus mu times d dt of, and now curl of H is equal to sigma E plus epsilon here times the partial of E with respect to T, right? Now here, I'm assuming sigma and epsilon right there are constants. If they weren't constants, what I'm showing you wouldn't work, right? And in truth, I got to caution you about something, because some of you will be working in this realm, probably from what I've been seeing. In plasmas, in the atmosphere, if you get above roughly 60,000 feet, the atmosphere begins to be a plasma. And things like conductivity are time varying, and they're also tensors. They're 3x3 matrices. Now, when you're doing any kind of involved radar work, or you're working with any kind of beams, particle beams or lasers, things like this, you have to realize if you're going through a plasma, it's a much different problem than going through free space, a vacuum, or something that's not a plasma. Just remember that for the future, because there's a lot of mistakes that are made by engineers because they don't grasp what their environment truly is in space. Space engineering, a lot of you guys are going to be doing stuff with satellites probably in the future. You're going to be dealing with a lot of things that are in space, and you have to be clear about one thing in your head, that environment is not like Earth. There's plasma up there, and it's all around. You always first look how the plasma affects the problem. All right, so this is the basic problem. Now I can spread that derivative through, and now I have gradient divergence of E minus del squared of E here is equal to, and now it would be minus mu sigma times dE dt, right there, minus mu epsilon times the second derivative of E with respect to T squared. And that is a single differential equation, still in time, right? that shows the relationship between the spatial derivatives and the temporal derivatives of the E field. Do y'all agree with that so far? Now, here's some things that I'm going to start simplifying this, and here's where I'm going with this. I'm going to get a single equation for this, but I'm going to go into the frequency or phasor domain, all right? And then I'm going to do something where I'm only going to be looking at the aspects of this that are related to plane wave propagation. Now that means if you're far enough away from the source of the electromagnetic wave, it all of a sudden starts looking like a constant, you might say, phase front. And there's no variation vertically or horizontally, just in terms the variation is only going to be radially away from the event that caused it. All right, now I'll explain more about this in a second. But if I'm at this point right here, now what I'm going to do is this. I'm going to say two things. First is that whenever I have a derivative with respect to t in the time domain, that transfers over to a multiplication by j omega in the frequency. Do y'all remember that? The best example of that was this right here. I knew the voltage across here was equal to L di dt, but in the phasor domain, what is it? L di dt becomes j omega L times I vector, and then V vector over I vector is the impedance Z, and it's just j omega L. Do you follow me on this, class? So here, now because this will be true, we take this equation, and anywhere there's a time derivative, we take a j omega out. So this becomes equal to the gradient of divergence of E minus del squared of E equal to minus mu sigma, technically j omega, times E minus mu epsilon, technically j omega squared, times E. Y'all follow me on that? Now we have an equation that is simply a spatially differential equation. There's no time form of it. It's just j omega there. This makes the solution much easier. Now here's the next thing I do. All right, I'm going to factor out E from there. So now I have minus, I'll put it, this is going to be minus j omega sigma mu, and then it's going to be plus j omega squared times mu epsilon times E is equal to this, which is gradient of the divergence of E minus del squared of E, right there. And now, let me do one other thing. Now, we're almost there, just hang on. Do you all remember what this, let me put it right here. Do you remember divergence of D is equal to what? Does anybody remember? How about the integral of D over any closed surface? What does that amount to? Anybody?
Charge enclosed.
Yeah, right. What law is that? Gauss's law, right? That's Gauss's law, right? Gauss's law. Well, this is the point form of Gauss's law right there. And divergence of D, instead of the charged enclosed, it's equal to the charge density. Do y'all remember that now? I mean, I hope you do. Divergence of D is rho v, right? Now what we do right here is we make an assumption, and because divergence of D is rho v, if I replace D by epsilon E, I get divergence of E here is equal to rho v over epsilon, don't I, class? And now we make an assumption at this point. We say we assume that rho v is 0, and because of that, divergence of E is 0. Now let me tell you why that's important. Right here in the atmosphere, there is no charge that's bound and stuff like this. It's charge neutrality. All right, there are negative and there are positive charges, but the sum total of the charge here is 0. Follow me on this, class? Air is down here is considered, rho v for this is 0. In general, the atmosphere assumes there is no charge density. Free space or a vacuum has no charge density. Almost every propagating problem you run into has no real bounded or free charge density. For instance, if an electromagnetic wave propagates through this wall, it's charge free. Do you follow me? Even though there are charges, both negative and positive there, the net sum of the charges is zero. Got me on this one? Now, where this changes is in a plasma environment. All right, that's where it changes. Just be aware of this. You're not going to get plasma problems in here for a while, but you have to be aware of that in context. So that means I can get rid of this, because if divergence of E, or if we assume this is an assumption, so just put down we're in air, all right, air, or the atmosphere. Then divergence of E is zero, and this gets rid of this, because the gradient of divergence, well, gradient of zero is zero. Do you agree with me, class? So it gets rid of that, got rid of one thing. Next, I'm going to get another piece of paper. The next thing I do is introduce a constant. So let me rewrite this. I have, and I'm going to move the negative signs around. I'm going to get rid of the negative. That's an omega times E. Here's what I've done. I've taken this right here and I've changed the negative, and then I factored out a j omega mu because they occur here and here. So you have sigma plus j omega epsilon by itself here times E. Do you all see what I've done, class? We're getting there. And here the assumption still is rho v is zero. It's charge free, or it's like in the atmosphere. Now we do something else. Everybody kind of getting where I'm going with this? I know this really looks cryptic and stuff like this because you're not used to dealing with del squared operators and curls and divergence. Not usually. You will by the time you graduate. You'll be very versed in it, but most of the time up to this point, you don't do a lot of that. I don't think. You got it maybe some in physics, but I don't think any mechanics courses use curls at all that you've had? Dynamics?
So that shows up in Calvary, but that's about it.
Well, Coriolis force is something that they often talk about in terms of curls. I don't know if you remember that back in the day. Well, I'll speak more about a curl in a bit. But anyway, we're at this equation now, right? Now, what we normally do here is introduce a constant. And this is called gamma, and this is the propagation constant. Gamma is equal to the square root of this, j omega mu times sigma plus j omega epsilon. And gamma is equal to alpha plus j beta. So this is a propagation constant. Alpha is an attenuation constant. And beta is called the wave number. Now remember, this is assuming that we're doing phasor analysis, so there's a sinusoidal source that's exciting this, so you're going to have waves, all right, constant frequency waves. It's important you keep that in mind, or at least for this analysis it is. Now the attenuation constant alpha is in Napier's per meter, and it really tells you how fast the wave's going to decay. I'm not there yet with the wave, but I'm going ahead of myself in a sense. Beta is the wave number. Beta is radians per meter. It tells you how many radians there are in a meter, or how radians of phase change. It's like phase changes, if you think about it with phase change, if you have a waveform like this and it's sketched and we freeze time, right? Well, that's 360 degrees, if you know what I mean, if it's a sine wave, right? There's 360 degrees of change, or 2 pi radians of change in that length, whatever that length is. Do you follow me? So that's, beta gives you that. It tells you how many radians per meter, how much change is happening per meter. 2 pi radians, 100 pi radians, whatever. Now, with that in mind, this equation becomes del squared, right, of E. And then I can replace this by gamma squared, and I can take it to the other side, and I get this minus gamma squared E is equal to 0. You all agree with me? I'm replacing that with gamma, and it's obviously squaring it, and then taking it to the other side. Now here's where we're getting to some plane wave phenomena. We're going to do something. E in general can be assumed to have an X, Y, and Z coordinate, right, component, I should say, in general. We're going to limit ourselves to electric fields that have only one coordinate, and that would be a coordinate in the X direction. So we're going to say only EX exists. And the second thing is we're going to assume that EX only varies in Z. Now I'm going to go to the board right here and try to explain a little something, because I'm cramped right there the way I'm doing this, and see if I can get this. I hate these kind of boards. These aren't true whiteboards. That's glass, and they do not work the way a whiteboard does. I found this out the hard way. I don't know why they put them in here, not just a whiteboard anyway. Here's what I'm going to get at. I want to try to show you this. Hopefully y'all can see it. What we're now talking about is going to be a wave that's going to be, or phenomena, electromagnetic phenomena, a long way from a source. So I always do this. Think of a pebble dropping in the water. And think of the height of the actual water being proportional to some electric field, all right? In this case, E field in the Z direction. Well, what you'd see is if you drop a pebble, you would see a ring of constant height there that would propagate out, right? And what you could do is say, if you wanted to take a look further and further away at how that propagation occurred, you would see a circular form. And then when you get way out here, where the radius of curvature all of a sudden becomes infinite, when you're far enough away from the source point, you can see that basically if you're over a relatively short distance, this becomes a straight line. There is no difference in the height or position here, or I should say the height of the waveform in here, and it's straight. You follow me? That's called a plane wave. So if you're a long way from the antenna that created the wave, for instance, there's a broadcast coming out of Columbus, Georgia. I'm here. Pretty much anywhere I measure the electric field from that broadcast over here, the electric field will have the same magnitude if I am at the same radial distance, right, from here. And it would be planar. That's called a plane wave. Now, when we deal with electromagnetic phenomena, when we talk about plane waves, we're also only talking about one component. So take this example a step further. Now we're a long way off, and let me erase this. Try to show you this. So now I'm going to look at the wave. I'm going to try to draw this for you and tell you what's going on. We've got an electromagnetic field propagating in this direction, the Z direction. I'll derive this in a second. The field has an orientation in the X direction. I'm about to show you that this value of EX here that we're going to derive can be expressed as this. If we assume plane wave propagation, we're far from the source, and the E field has only an X component. It will be equal to some E naught, call it E naught here, and it would be E to the minus gamma Z, or it would be E naught, E to the minus alpha Z times E to the minus J beta Z, all right? And that's in the X direction. Do you follow me? Now I'm going to show you how you get that from this without driving you nuts, hopefully. By the way, class ends in about 3 minutes, right? My watch isn't that slow. All right, follow me on this now. When we take this right here, generally speaking, the del squared operation is equated to derivatives with second derivative with respect to x, and a second derivative with respect to y, and a second derivative with respect to z. And that's a vector operator, so that operates on both the x, y, and z components. Do you follow me in that, class? Now we only have an x component, so it's only going to be derivatives with respect to x. Now listen carefully. When I do this del squared of e on only ex, right, I get the derivative with respect to x. Now what did I say it varies with? Only with z, right? So the derivative with respect to x would be 0. Right, if there's no variation. The derivative with respect to y would be 0 as well. I've made the assumption it's only propagating in the z direction. Do you follow me in this class? Now the derivative with respect to z, though, that's going to exist, so that means this del squared operation would be the second derivative of ex with respect to z squared. That's going to be there. So now this equation right here would become second derivative of ex with respect to z squared minus gamma squared ex equals 0. Are you with me? I'm just going to tell you this right now because we're a little short on time. I can go through the separation of variables model for this later, but right now I want to tell you this is a general first order differential or second order differential equation. It's homogeneous. The solution for this will be ex will be equal to some ex plus, or e0 plus, it's fine, times e to the minus gamma z, and it's going to be plus e0 minus times e to the plus gamma z. This was a waveform traveling in the plus z direction. This represents a waveform traveling in the minus z direction. Does everybody follow me on that? Now, I can, if I had more time, I could take this and show you how we can go to the time domain form. But what this amounts to is the general solution for an electric field derived from Maxwell's equations with the assumption that the charge density is 0 and the electric field has only one component and it's propagating in only one direction. Believe it or not, this is something that is applicable to many, many situations, and that's why we start there. And it's in the phasor domain. And I'm out of time. Do me a favor. Does everybody have this book again? Anybody not have the book? Good. I don't have to order it. All right. Make sure, I would suggest if you can, bring your book to class next time. I'll try to remedy this mess here so I can use the board and try to make it clear to you. And I'm going to give you some homework. It's going to be very basic on this, all right? And make sure you do it. This is a huge class.
So I can get to one, but I don't know if that's a setting that you have to